Good morning from Democracy Research Center in Athens. Do you know what this is? It's actually a cable, a fiber optic cable for transporting information, transmitting information with a laser, with light. In actual fact, a cable like this would be a very long cable, could be hundreds of meters long, even thousands of meters long. And the remarkable thing is that light and information, data, can be sent over kilometers just using the glass fibers that are inside here. In this particular one, there's 3 different types of glass fibers, and I'll show you that how it works. I'll just send a laser beam. There's a laser here, a laser beam. I'll send a laser beam from one side, and you will look at what comes out from the other side. There you are. I think you can see that there are 3 different fiber optics cables, fiber optic fibers. Okay, so the remarkable thing is that this is a bent fiber optics cable, and yet we know that light always travels in a straight line. Light always travels in a straight line. So how is it possible that we can actually send the light in a bend? How do we bend light? And the answer is a phenomenon in physics called total internal reflection. Total internal reflection happens when light tries to go from a solid, a material where the speed of light is lower than through another material where the speed of light is higher. Now, speed of light, as you all know, it's constant, and it's always about 300,000 kilometers per second in vacuum. In air, it's slightly less, but in material like glass, it can be quite a lot less. We describe that with the index of refraction. The refractive index is a way of describing the speed of light through a material. It's not exactly that. It has to do with geometry of refraction and through interfaces, but we can think of it as a way of describing the speed of light in a material. Now, this is glass. The glass fiber here is made of a very high quality glass, so there's no absorption of the light. We don't want to lose light, even though after a kilometer or so we have to have an amplifier, so where they join with a small amplifier, light amplifier, but anyway, that's a detail. But you can also have a total internal reflection through many different materials. For example, this one here is a perspex. It's a PMMA, that's polymethyl methacrylate. You've seen it all, a perspex, or sometimes called plexiglass. And here it is. If I send the beam through there, a lot of it is actually absorbed by the perspex. That's why you see it green over here. But a lot of it, and most of it, will come out the other side. Just like the fiber that we saw a moment ago. If I send it from this side, it will be the same thing. Some of it will be absorbed, and most of it will come out the other side. This is now a perspex, and of course, this little toy, this little beautiful design, this is made of many different fibers. There you are. We can switch off the light, and you can see the fibers over here. This is green. There's an LED light down there which changes colors according to the voltage that you put it in. Anyway, it's a small detail. And each one of these fibers is actually an optic fiber, and it transmits light that comes from the LED. It's very beautiful. It's actually a very nice toy, and you can have it in your desk, and you can really enjoy it like that. There you are, red and purple and blues and everything. So these are materials that transmit light, and as I said, the reason is because the refractive index of these materials is greater than that of air. Refractive index of air is about 1. This one's here, the plastic, is about 1.4. Glass can be 1.6, 1.7, the glass fibers, and the ultimate one is diamond, and the refractive index of diamond is nearly 2.3, I think, 2.4, and it's really, of course, it's very difficult to make any fibers out of diamond, but we do have fibers out of ceramics with a very high refractive index. Now, how does it actually look? When you say that there's a total internal reflection and that allows the transmission of light, we have a nice demonstration here. This is water, and this is sitting in a glass, and of course here we have a double interface. We have the water going into glass and the glass going into air. So if I shine the laser through the water will allow transmission to the glass, but as soon as it reaches the air, where the refractive index is lower, it will reflect back. So if we can switch off the light, and you can see how beautiful it is. The laser goes through the light, goes at the interface between glass, the water and the glass, it goes through, and at the final interface, where it's glass against air, it reflects backwards, and you can see there's actually two reflections. One is about here, and the other one is down here, and it really is quite a fascinating little demonstration of total internal reflection. You can think of this as a short length of fiber optics, and that's exactly how the light is transmitted. Whenever there's an angle, whenever there's a curve in the fiber optics cable, it just reflects. This one here, I made a triple reflection. That's a very nice one. One right up here, one down here, and one over here as well. And you can see that the light goes right through this, but because of total internal reflection, it does not allow it to go anywhere, and it completely stays within the water within this tube, this vase. Okay, so finally, we've been talking about glass, we've been talking about air, the difference in refractive index. What happens with air on its own? Is air a good medium to demonstrate total internal reflection? And yes, it's a lovely little experiment. You can see it in many other experiments, many other types of videos in the internet. And I'll show you over here and show you some interesting. If we have a bottle of water, I put the laser over here, switch it on, and allow the laser. I've made a little hole over here, and allow the laser to go through the hole. There you are, a little bit higher. There you are, it's going through the hole. See if I can get it right in the center. Here you are. And now, if I allow the water to run through, the laser actually, you can switch off the light, the laser actually follows the flow of the water. It's really beautiful. You can see it very clearly that the laser is following there on my hand. You can actually wash your hands with green light, a very beautiful green light. It almost looks radioactive a little bit, or something out of a science fiction movie perhaps. But it's very, very pretty, and you can see the water is actually, the laser light has total internal reflection within the flow, within the flowing water. And if you can see the details, you can see that some spots, they're green spots, that's where the reflection takes place, or the laser reflection. It really is quite fascinating. So this is now the total internal reflection, and if, of course, as I said, the refractive index is what decides on the critical angle, the angle that will allows the total internal reflection to take place. And with this, I hope you understand now that the fiber optic cables that allows us this extremely fast data transfer would never be possible without this the phenomenon of total internal reflection. It's something physics has solutions, gives opportunities to many different things. And you and I you wouldn't be able to see this video at this moment without fiber optic cables. Until next time, goodbye from Democritus.